And then I'm going to project to your screens, I hope, in just a second. All right, so you may want to set your monitor for full screen so you can see a little better what's going on here. All right, so what I really want to project first, though, is this little PowerPoint slideshow that I have right here. So let's go back to this. All right, so hopefully you can see on your monitor a ruler, which we call a scale, and this is the engineer's 10 scale. And we have 3 different measurements marked off on this, and I'm going to discuss all 3 of those measurements here in just a second and kind of get into detail with those. So let's say that you have a dimension of 3.125. We would say that this dimension has 3-place precision, and we've already talked about precision. Whenever we set up a dimension style, we go in and we choose the precision we're going to use. And for most of our projects so far, we've just used 2-place precision. And then when we needed 3-place precision, we just edited a 2-place dimension and made it 3 places. So we would pick on it, right-click, choose precision, and then choose the 3-place option. So to break down, a dimension like this, the first number, the one to the left of your decimal place, is whole inches. Now, it's possible if we were doing a metric drawing, that could be millimeters as well. But in this case, we're just going to think of these as inches because the 10 scale is set up for measuring inches. So we have 3 inches, and then we have our decimal point, and then to the right of the decimal point is our placeholder for tenths of an inch. So if we took an inch, divided it into 10 parts, that's what this would represent. Our second placeholder would represent hundredths of an inch. So if we took a tenth of an inch, we divided it by 10 parts, we would have 100th of an inch, right? Then our third placeholder is 1,000th of an inch. And 1,000th of an inch seems like it'd be really small. So imagine you've got 1 inch, you divide it into 1,000 equal parts. Well, those are pretty small. But it is kind of conceivable. I'll give you an idea of what a 1,000th of an inch dimension would look like. If you had a piece of printer paper, I'm just talking about common printer paper, and you put it on a tabletop and you put your finger on it, and then you rub your finger over the edge of it so that your your finger dropped down to the tabletop, that little bit of distance that you would feel, that difference between the top of the paper and down to your tabletop, would represent approximately 0.004 inches. So a sheet of normal printer paper is about 4/1000ths of an inch thick. All right, so that gives you some idea of kind of 1,000. So if you could take a piece of printer paper and shave it into 4 different pieces through its thickness and just take one of those, you would have 1,000th of an inch. So you can actually feel 4/1000ths of an inch pretty easy. You can feel the difference in that. So let's look at our engineer's 10 scale again, and let's look at something taken to 1 decimal place of precision. So we have 1.5 inches. So this is purely tenths of an inch right here. It's 1 5/10 inches. And so each of these marks represents a tenth of an inch. So we go to 1 inch, and then we count over 5 more. So there you go, 1.50. Now, we have another dimension here that's 2.75. So this is 2 inches, and it's 7/10ths of an inches plus 5/100ths of an inch. So we can go to the 2 and then count our 7/10ths, which would get us to right here. And then we'll count our 5/100ths, which would actually be halfway between the 7th tenth mark here and the 8th tenth mark there. So we would call this 2 75/100ths inches. All right. Now, this guy we've taken to 3 places. So we go to the 3 inches, we go to our 1/10. You know, I realize I don't have a pointer up. Let me get a pointer out here. Make this a little bit easier. So we're going to take this to 1/10 of an inch, which would be right here on our 3.1. Then we're going to go 2/100ths of an inch, and then we're going to go 5/1000ths of an inch. So remember I said a piece of printer paper is 4/1000ths of an inch, so this is just slightly more than that. And you know, we happen to know that 0.125 equals 1/8 of an inch if we were in fractional inches. So this is a pretty common measurement, 3.125. So we have 1-place precision, 2-place precision, 3-place precision. We call this 1.5 inches, 2.75 hundredths inches, and 3.125 thousandths inches, or we can just say 3.125. That's usually what designers will say. Okay. Now, in manufacturing, usually, especially in North America where we're working in inches or the imperial system, we generally break things down into that tenths, hundredths, thousandths of an inch increment. So here's 4 inches broken into 1/10 inch increments right here. Okay, so let me get to this slide. So here we have tenths of an inch, 5/10ths, 1/10. These are pretty easy to understand. The concept of breaking an inch into 10 equal pieces and calling those a tenth of an inch. But what if you took a tenth of an inch, like we've got right here? That would be the distance from here to here. And you broke that down into 10 equal parts. Those would represent hundredths of an inch. So if you had 52 hundredths, you would count your tenths first. 1, 2, 3, 4, 5, because that's what you're seeing right here in the tenths place. Then you would count 2 more of those smaller increments, which are hundredths of an inch. And so this is what 0.52 would represent. And of course over here when you just have a tenth of an inch, each one of those is 1/10. So 10 1/100ths of an inch is written as 0.10, where a tenth of an inch is written just as 0.1. So here we have 52 hundredths of an inch. And this would represent 2-place precision. All right, now I want you to imagine that you have a tenth of an inch, which is right here. And then you break that tenth of an inch into 10 equal parts. Each of those parts would equal 1/100th of an inch. Then I want you to imagine that you take one of those 1/100ths of an inch increments that you have on here, and you divide that into 10 equal parts. And what you would wind up with is what we see down here. This is 1/1000th of an inch. All right. So, like I said, this would be a piece of paper sliced into 4 thicknesses, through its, longitudinally through it. So that would represent 1/1000th of an inch. Okay, so we have 100th of an inch, which is this up here. And 1/1000th of an inch is written as 0.001, it says right here. And the fundamental unit of measurement for a lot of machinists, especially in the United States, is 1/1000th of an inch, because their mills and their lathe set up down to 1/1000th of an inch. That's pretty common that they can set their mill or lathe in the 1,000th inch range. And for this reason, here's an important concept. Machinist will refer to 1/1000th of an inch as 1 thou. Okay, so 1 thou, this is kind of an important concept. So what we have right here, when we have 0.001, like what we have right there, a machinist would say that's 1 thou, or 1/1000th of an inch, right? But by the same token, if you were talking to a machinist and you were thinking that your tolerance was 1/100th of an inch, what the machinist would do is almost certainly go ahead and add another 0 to that, the way that they conceive of 1/100th of an inch. And they wouldn't say that your tolerance is 1/100th of an inch, like what you're seeing right here. They would say that your tolerance is 10 thou. And they mean exactly the same thing as when you say 1/100th. Because 1/100th of an inch, this guy right here, if you put a 0 next to it, represents 10,000th of an inch. And so if you ran a machine that's set up in thousandths of an inch, you wouldn't be thinking in hundredths of an inch. You would think in thousandths of an inch. And that's why machinists do this. The problem is that in the engineering office, a lot of times we're thinking our tolerance is 1/100th of an inch. You walk through the door of the machine shop and they're throwing back to you that it's 10,000ths of an inch, but it actually means the same thing. So I just want to make that point to you guys while you're in 1405 so that you understand this thou language that you're going to hear from machinist. Okay. So, of course, when you go 0.000, you're talking about 3-place precision. Now, you can break 1,000th of an inch into 10 parts, and then you wind up with 1/10,000th of an inch. And, that's really small. So if you were tolerancing your parts to a 10,000th of an inch, those parts would probably cost a fortune to make. So most people will avoid going to 10,000th of an inch unless they're making something that has to be really, really precise. Okay. Now, when a machinist, though, sees a dimension like this, so we've got tenths, hundredths, thousandths, 10,000ths, a machinist calls 1/10,000th a tenth. And so we're kind of trained that anything that's right here in that first slot, that is 1/10th of an inch. And it is. That's 1/10th of an inch. But to a machinist, a tenth is 1/10th of a thousandth. And so that's why they use this word tenth. So you have to be careful that you don't get confused between a tenth of an inch and a 10,000th of an inch when you're speaking with machinist. So those are just things to consider. So like we say here, this is an example of 4-place precision. All right. So I'm going to skip through, and there's one I wanted to point out to you here. This is kind of a review of what I just covered, but I want to point this one out to you right here. Let's say that you have a 0.955. So that's 955 thousandths of an inch. Well, that is the diameter of a quarter. All right, so everybody probably knows what a quarter is, right? So a quarter is not quite an inch in diameter. In fact, it's 45 thousandths of an inch smaller than a full inch in diameter. So 0.955, just to relate it to something that's pretty common to us all, that would be the diameter of a quarter measured very precisely. So if you said that the diameter of a quarter was 0.9, you would be off by 55 thousandths. If you said it was 0.95 in diameter, you would be off by 5 thousandths. So you'd be off just about the width of a sheet of paper. So you can see how it's getting smaller and smaller in your amount of error that you have. Okay. So back to tolerancing. What is tolerancing? So when we manufacture parts to an extreme degree of precision, it's difficult and it's expensive. So what designers do, they calculate how much the size and location of a part's features can deviate from the dimensions specified on the drawing and still perform their design function. This is what a tolerance is. It's like this allowable error that you give to a machinist. So the more error you can give a machinist, the more leeway you can give a machinist in how precise a part has to be. Generally, that part will cost less to manufacture. And so the amount that the size or location of a feature is allowed to vary from its perfect size and position is called a tolerance. All right? And everything is going to have a tolerance. So I'm going to skip through here for just a second to this guy right here. So we are following a standard called the ASMEY 14.5-2009, And this is the dimensioning standard that is established by the American Society of Mechanical Engineers. And if you went to work in an office in a machine shop, it's possible that when they're giving you your orientation, they would tell you that in this shop we use the ASME Y 14.5 standard when we're dimensioning and tolerancing things. And so you would nod your head knowledgeably. And the reason you could do that is because when you're trained over here at ACC, we decided years ago that we would use this standard in our classes, even though most colleges don't bother to do that, because we wanted you to walk out of here when you graduate with an idea of what the ASME standard is like, because we think it's valuable and we think it's something that you should bring up in a job interview. It's that valuable that you've actually worked with this standard. I want to show you something about this standard though. Here's what the ASME standard says about tolerancing on mechanical parts. It says each dimension shall have a tolerance except, and then it gives you a few things that you don't really understand yet. We're going to talk about some of these, but let's just take that first part of that sentence right there, that each dimension shall have a tolerance. So that pretty much, that's a rule right there. And I'll tell you how I know it's a rule. You see right here, they say each dimension shall, okay? So the way I look at that, shall is biblical. And whenever you see a biblical term, it's probably important, okay? So that's how important tolerancing is to ASME. Now the reason you want tolerances is this. If someone makes a part for you and then they want you to pay them for that part, and you measure the part and you find that that part is off by 1/100th of an inch from your drawing, do you owe them the money for making that part? They can say, hey, you didn't specify how exact that part has to be, and you can't really expect people to make exact parts. So you would be in this argument about, do I have to pay for this part? At what point is the part too far out of tolerance? Well, if you had made a drawing that had tolerances on it and you gave it to the manufacturer needs to make the parts within those tolerances. If they do that, then you owe the money for that part. If they're outside the tolerance, you wouldn't owe the money. That's what you would put into your contract with the manufacturer. So this becomes contract language between organizations. So it's really important. And so tolerances are a really good thing. And here's why. Designers like tolerances because if you manufacture the parts they designed within the tolerance, the parts should work in their function. Manufacturers like tolerances because if they make the parts within the tolerance, then their customers would be required to buy the part. So it's a good thing for both parties, and it clears up a bunch of stuff for both parties. Okay, so here's the takeaway. You shall have tolerances, and tolerances are good. Okay, so we'll get into some more of that right there. Let me see. Here's an example of a tolerance on a part. So if you dimension this part and you said that from this plane here to this plane here, when that's measured, as long as it falls between 1 inch plus or minus 1/100th of an inch, that feature right there would pass inspection. So when this part is inspected, they would measure the distance from the top plane to the bottom plane. And there's some really sophisticated measurement instruments out there now, or you could even use a micrometer or a caliper, which is a handheld thing. And even those have become digital, so they're very accurate. So if you measured and this part fell between 1.01 in height and 0.99 in height, then that feature, this distance from top to bottom, would pass inspection. The next feature you would probably measure would be the width, and it would probably have the same kind of thing. It might say 1.00 plus or minus 0.01, and then the person inspecting the part would measure that second, and if that fell within tolerance, they would just keep following. They would keep measuring the dimensions that you had put onto your part, and they would keep checking if it were in tolerance. If everything they measure falls within tolerance, then the manufacturer's made a good part, and you're going to pay for the part because you know it's going to work, because you've designed it within those tolerances. You can have the same thing in the metric system over here. You can have 25.4 millimeters plus or minus, and in this case it's 1/10 of a millimeter. All right. Excuse me. The next little bit of information here, where it's circled that 1.00 and it's circled the 0.25, what we call that dimension that you can add or subtract your tolerance to, we say that's the nominal size of the part. So the nominal size of the height of this part is 1.00. So a definition of nominal size is it's the size that you can add or subtract your tolerance to, or apply your tolerance to. All right. So the next thing that gets circled here is this guy right here. This is actually your tolerance. That's the allowable degree of error that you're going to give the manufacturer. Okay. So does anybody, you may have a question. If not, I've made 3 videos that are in Blackboard that I'm going to point you to that will go over what I'm talking about in greater detail. And I think they're really important videos to watch, because if you want to become a designer, you've got to start thinking like this. Now, most of you, when you came into the class, maybe you thought, well, this is going to be a technical drawing class. I'm going to learn how to make, technical drawings. It is, but what I think is that, you really can't understand dimensioning until you understand what goes into the calculation of those dimensions. And what goes into the calculations of the dimensions is tolerances. Okay. So let's go over here. Here's another way you could write a tolerance. This is called a limits tolerance. And in that one, you just go ahead and straight up say, hey, as long as this part falls between 101 and 0.99, that feature right there would pass inspection. Same way over here with our metric limits of size. So we have an upper limit of size and we have a lower limit of size. So a limit of size is the maximum and minimum size of a feature as defined by the tolerances. Okay, so now you're going to have to put on your thinking caps just a little bit. This is a really simple example of how tolerances and dimensioning all come together in a drawing. So I want you to tell me what the width of this slot is right here. Now, you don't actually have to tell me, but I want you to look at these 3 dimensions right here and say, what would the width of that slot be right there? Okay. So if you start at this datum feature over here, which we have right here on the edge, and we measure over 1, and then we come back to that datum feature and we measure over 2 inches, that defines our slot. So our slot would be 1.00. And the way that we've dimensioned this part is what's called a baseline dimension. What a baseline looks like is this. You define a baseline feature, and in this case it's this plane right here, and then the dimensions all come off of this baseline right here. So we have our 1.0, our 2.0, and our 3.0. They all reference this baseline edge right here, which some people call that a datum. I think of it's an edge, it's a datum feature actually, but that defines that our slot is 1.00. So again, this is called baseline dimensioning because we're coming off of this baseline over here. The alternative to baseline dimensioning is called continuous dimensioning, and I want to show you how it works. We have a datum feature over here that we start from, and we dimension to the first side of that slot, and we go 1 inch, and then we dimension from the edge of the slot to the opposite edge of the slot. You can see the difference in the two, but how wide is the slot? Well, it is purely this dimension right here. It's 1.00. So whether we dimension it using baseline dimensions like we have up here, or whether we dimension it using continuous dimensions, the width of the slot is 1 as long as we don't have tolerances on it. So that's the key thing. Once we add tolerances to this, the widths of those slots is going to start to vary. So as a designer, this is like design 101 right here. What would the width of the slot be if we started to add tolerance to those things? So that's what the next slide shows you. I'm going to go to the next slide right here. Okay, so now we have tolerances applied to our part. This is still baseline dimensioning. And what I hope to show you is there's even a difference in the tolerances when you apply baseline versus continuous dimensioning. So let's look at our first dimension. It's 1 plus or minus 0.01. So I'm going to imagine then that this part could be 101 or 0.99. I'm going to imagine that the manufacturer makes that first distance from the datum feature to the edge of the slot at 0.99. And then they look at their next dimension up here and says you can make that as far as 2.01 or as narrow as 1.99. So let's say that they push that and they go to 2.01 over here. Now, what's the width of the slot? All right. So what you do, you would take 2.01, because that's how far this edge is out, and you would subtract 0.99 to see what you have left in here. And what you would find out is that in this case, the width of your slot, because it's toleranced and you're using baseline dimensions, comes out at 1.02. Where on the previous slide, when there were no tolerances, the slot was exactly 1.00. Okay, so now we're going to compare baseline to continuous. So I'm going to go to the next slide. This is your next slide. So we have tolerances applied to these numbers now, where before we didn't. So this time, let's do the same thing. Let's imagine that they go 0.99 on this side. So that would mean that this edge is pulled back 1/100th of an inch from its nominal size. Nominal size is 1.00. The limits of size would be 0.99 or 1.01 if we add or subtract these two guys here to the nominal size. So let's say that they make this 0.99 like they did up here. Well, when they made this 0.99 up here, it actually affected our tolerance. But if they make this 0.99 or if they make it 1.01, does it affect the tolerance of this slot? The answer is no, because the width of that slot is being controlled by this dimension right here alone. Okay, you see the width of this slot can only be 1.01 or 0.99. It can't get wider or smaller than what the tolerances say right here. So let's say that they make this at 0.99. They make the slot the narrowest. You see how the difference between, we said up here that our slot, because of the way that these like two different tolerances affect the width of the slot, we said that this guy could wind up being 1.02. And if we had gone the opposite direction, if they had pushed this in and they made it 1.01 on this side, and then they pulled it on this side, and they would be at 1.99, the narrowest the slot could be up here is actually 0.98. So because we have two tolerances affecting the width of the slot, Here's the widest the slot can be. Here's the narrowest, 0.98. Down here, the narrowest the slot can be is here, and the widest the slot can ever be would be 1.00 plus 0.01. So the widest would be 1.01. That would be the other limit. That would be widest, and that would be narrowest. So you see the difference between the slots, and that's all based on how you dimension it. The reason I'm showing you this is this. I want you to imagine, let me go to the next slide here. Let's see what happens. We go to the next slide. Looks like I'm going to have to just back up. I think it's going to save my marks, unfortunately. I need to clean my marks. I don't know if I can just knock them right off of this one. There we go. Okay, so here's the thing. Let's say that a designer hands you something to draw, and the designer has dimensioned it like this, like the one on top. And so you think, you know, I'm smart, and you say, you know what I'm going to do? I'm going to dimension it like this because that's the same thing, right? Well, hopefully what I just proved to you is it's not the same thing. So if the designer sketches their part like this, you can't change the dimensioning style. You need to use baseline dimensioning because that will affect the width of the slot. Like I said, the width of this slot would be 0.98 to 102, dimensioned like this. Where dimensioned using continuous, the width of the slot would be 0.99 or 101. So what you would have done by changing your dimension style is you would have changed the designer's intention or design intent. And when you change design intent, you get in trouble. Because think about, like when a car company builds a car and then they find they have to do a product recall because the windshield wipers don't work right or something. And they have to replace the windshield wipers on 100,000 cars. That's pretty expensive. If they had caught that before it got out, it would have been a lot better. So how do we specify tolerances on a drawing? Well, one way is to go to our title block, and then we change these numbers here to match whatever our designer tells us those should be. And so in this case, anything that's taken to one decimal place on our drawing. So let's say that we have a dimension that goes 1.0. That would have a tolerance of plus or minus 0.05. That's 0.05 of an inch. That's really a generous tolerance. So it would mean the designer doesn't really care too much about the precision of that. So that would be less expensive to manufacture. But let's say the designer puts a dimension on there that says 1.00, and we look at the tolerance block here, then now our tolerance that applies is plus or minus 0.02 of an inch. It's a tighter tolerance than what we had before. But let's say somewhere else our designer has 1.000 on their sketch. We need to write 1.000 on our drawing because things taken to 3 places could have a tolerance of 1/100th of an inch or 10,000ths of an inch, which is the same thing. All right. So we need to follow exactly the same precision that the designer does. Okay. The other thing we want to make sure that we do, I'm going to back up, is this. If the designer is dimensioning from this side of the part, you need to dimension from that side of the part too. Don't move over here and start dimensioning in this direction. Okay? That would be changing design intent because the designer has calculated everything off of this side over here. Now this part's symmetrical, so it's kind of hard to tell which is the correct side, but let's say that there were a hole just on this side right here. Then you would know for sure that you have to dimension this off of this side for this part to work. Okay, so what I'm going to do is I'm going to switch over to AutoCAD real quick. because we are going to bring this all back to AutoCAD. All right, so what I made is a dimension style where I have my tolerances turned on. I'm going to show you how I did that. You pick on your dimension style tool right down here, and this opens up. And so I took my ASME small radii and I chose new. And what it did is it took the ASME small radii and it made a copy of that. And then right up here, I typed toleranced. I wanted that to be the name of my new dimension style. And then I picked continue. Now I'm actually not going to make another one because I already have one named tolerance. So I'm just going to pick on tolerance. And then I'm going to pick on modify so you can see what the settings are like in tolerance. Everything in the tolerance dimension style, like the lines tab, symbols and arrows, text and fit, and primary units, is exactly like the ASME small radii dimension style. The only difference that I made to it is I picked on this tab right here that says tolerances. And normally that is set to none. But what I chose was I'm actually going to go limits on this guy. And I'm going to set a limit of 0.01. So it could be plus or minus plus 0.01, or the lower value would be minus 0.01, and pick OK and close. Now I'll show you what happens when you do that. I'm going to dimension this hole right here. So we pick on the diameter for the hole, we bring our diameter out, and now we can actually see the diameter of that hole with its limits of size. So now we know the greatest this diameter could ever be is 1.01, and the smallest this diameter could ever be is 0.99. All right. So what if you were a designer and you were designing a cylinder to fit inside that hole? What size would you make that cylinder? Well, let's say you make it 1, just like this guy is right here, and then let's put a dimension on it. All right. So here's the problem we would have. This hole can be as small as 0.99. The cylinder that fits in there could be as small as 0.99, but it could also be a lot bigger than that. And at that point, the cylinder would not fit inside the hole, at least not without a hammer. Okay. Now, if we really wanted to hammer that thing in there, that would be okay if that was our intention, was to get like a mechanical force fit. That would be okay. But the point of that is that if you're a designer, you don't dimension the hole and the cylinder to be the same size. So let's do something. I'm going to erase that guy out. And I'm going to draw it a little bit smaller this time. I'm going to do a circle. And this time I'm going to draw, for my diameter, I'm going to draw 0.98 and press enter. And now I'm going to dimension that. So if the nominal size is 0.98 and I have a tolerance of plus or minus 0.01, the largest this hole could ever be is 0.99 and pass inspection. And the smallest it could ever be is 0.97. So let's look over here at this guy. Let's say they make this hole at the smallest. They make it 0.99. They make this hole at the this cylinder at the largest diameter. Would it still fit in? Well, the largest diameter is 0.99. Pardon me. Would a 0.99 cylinder fit into a 0.99 hole? Well, what you do is you subtract the diameter of the cylinder from the diameter of the hole, and as long as you have 0, you don't have an interference. So in theory, this 0.99 cylinder could fit into that 0.99 hole. You would have to line it up exactly. It couldn't have any attitude to it, any tilt to it or anything in order to get it to fit. So it would be a really snug fit if you tried to do that. All right, so let's try this. What if our designer then says, okay, you know what? I'm gonna make my cylinder 0.97, And now let's put a dimension on that. Okay, so let's go back over here. The smallest the hole could ever be is 0.99. By starting with a nominal size of 0.97, the greatest size of the hole, the cylinder would be 0.98, and the smallest would be 0.96. So if the largest this cylinder ever was 0.98, and the smallest this hole ever is 0.99, we actually have a clearance of 1/100th of an inch. So if the designer wants to make sure that it's pretty easy to fit the cylinder into the hole, then they would want to make it where that the cylinder would come out smaller or the hole would come out larger, one or the other. Okay? So this is a real simple example of what designers go through when they're designing parts to make sure that after the parts are made, they will all fit together. Because if we make 10,000 of these guys right here, and we make 10,000 of these guys, and then we find out that this cylinder won't fit, and we've already bolted those onto 10,000 cars, we might have to do a product recall, or something like that. So this is why designers make more money than drafters, because they are charged with figuring out these things. And it's really it's a much more interesting job also when you're actually designing things and trying to determine, are they going to fit together or not? All right. Now, I want to show you something else about tolerances on this part right here. This seems like a really simple part, but we already know that the diameter of the hole might not be exactly 1.00. It could be 101 or 0.99. But I'll show you something else that's weird about this. Let's say that you're trying to locate the center of that hole, and you measure from this datum feature over here, and you measure to the quadrant. Well, if you have a tolerance applied, that means the center of this hole from left to right could land anywhere between 101 and 0.99, and that would pass inspection. So not only is the diameter of the hole variable, the location of the center from this edge across in this direction also has a tolerance. So it has a variable. And then if you dimension from this datum edge down here on the bottom to the quadrant of the hole and move that out here, it also has to have a tolerance. Remember, ASME says every dimension shall have a tolerance. So there's your tolerance on that. So you have to imagine that the center of this hole is not going to be exactly at 1 inch from either of these edges. It also has a little bit of plus or minus to it. So what I want you to imagine is, let's say that they make this hole, or they place that hole and it's off just a little bit, but it's still within its tolerance. Then you make another one of those parts and it's off just a little bit, but in a different direction. And then you have to put two of those parts on top of each other and run one of these cylinders through it, like a bolt hole or something like that. You can see how pretty soon it's easy to have mistakes where things don't line up. Okay, so one of the things I usually will like to show students, I'm going to go back. I'm going to make these lines thinner so it makes it a little bit easier. If you were to offset this edge right here 1.01, so I'm going to offset that guy 1.01. You can see there's that offset of 1.01. And then I'm going to press enter, and I'm going to offset this 1.01. You can see where that red line hits. So there's true center right there, but now there's a 1.01 and there's 1.01. Now I'm going to offset, set my offsets to 0.99, and let me do an offset. Pick here and up, and then pick here and up. And then I'm going to do a trim. Let me get rid of all these guys. You see that red square? The center of this hole can fall anywhere inside that red square, and the location of that hole will pass inspection. Okay, that's how far off the hole could be. So that could mean that we could have one of these holes drilled right at that corner right there. And let's say that the diameter is 1. You see how eccentric that hole is right there, how it pushes it? The next part they make, we could have a hole drilled right at that corner as its center, and it being 1. And look at the locations of our holes, how they're starting to move around. So the perfect hole that we kind of have in our head, actually, because of tolerances, is not going to land perfectly. The more perfect we try to make it, the more it's going to cost. And this is the dilemma that a designer has. Okay. So there's a class called DFTG 1433. It's called Mechanical Drafting. And you can take it next semester. And DFTG 1433. And in that class, we get a lot deeper into tolerancing. Because really we teach you, the basics of tolerancing and designing in DFTG 1433. So it's a really cool class, I think. And it's one that I usually teach, but because of the pandemic, I don't think I'm going to be teaching it next semester, but I usually invite my 1405 students to take the class with me, because you're already used to my dimensioning style and everything, or else don't take it from me if maybe you've learned in this class you don't want to take it. But anyway, I'll probably teach it again next fall, but I don't think I'll be teaching it in the spring. All right, so I want to show you something else. I'm going to put a dimension from this corner to my center of my part like that, and then I'm going to put a dimension from the center of my part here to this edge here. Okay, so what is the widest that this part could ever be? Well, it could be 2.02, and the narrowest the part could ever be would be 1.98 if we added that and that. If this is how this part had been dimensioned, let me put that hole back in here. All right. So what if you came in here and you did a dimension from this corner to this corner, and you did that right there? Would that be okay to do? All right, so I want you to think about it. Right here, you're saying it's okay to be 1.01, and then from there, it's okay to be 1.01. So we know if we add those together, we're going to be at 2.02. But down here, we've got a dimension that's saying, no, you can't do that. It's got to be 2.01. Well, the truth is, you can't do this. All right? So if you want to do this, you're going to have to take one of these out. If you do that, you can do that. Okay, you can go 1.01, and then you can leave this blank, and then you can go 2.00. Or you can have both of these, and you can get rid of this guy like that. Or if you want to keep that guy in there, what you would do is this. I'm going to double click on this. You would have to type 2.00 and put the entire thing inside a parenthesis. So you would take this out right here. So let me change my dimension style and show you what I mean. Let me erase this first. Come on. All right. Now I'm going to set my ASME small, set it current, pick OK. And now I'm going to put a dimension from here to here. All right, so obviously this couldn't be 2.00 if this is 101 and this is 101, or this is 0.99, this is 0.99. So what we do is we put this in parentheses. When you put a dimension in parentheses like that, it makes it a reference dimension. And what we're saying to the person making this part is, make the part using this dimension and this dimension. That this dimension down here is just for reference, and so don't make the part, don't apply tolerances to it, or don't inspect it using this dimension right down here. So anything that's in parentheses is a reference dimension. And so a minute ago when I was reading that ASME thing that said every dimension shall have a tolerance, and then it said except, and then it gave you a few things that don't have to have a tolerance. One of the exceptions was, it said, except a reference dimension. It does not have to have a tolerance. So this is an example of a reference dimension. And so I want to point out to you on this drawing right here, when you see the check print on this drawing, we actually have a reference dimension right over here for the overall height of this part. Now, why is that? Why does this have to be a reference? Well, here's why. You're given this dimension right here, and that would have a tolerance. And then you add this dimension to that, and this dimension will have a tolerance. And then you're given this diameter right here. Okay? So if we take half of that diameter, that would be the distance from the center mark to the top, and that would have a tolerance on it. So we actually have 3 dimensions that give us the overall height. So that's why if we give the overall height, we have to just give it as a reference, because those 3 dimensions that we've given would have tolerances on them. And so there's no way that we could just have this without this being a reference dimension. So if you handed in your drawing to me and you had 12.7 and 63.5 and you had the diameter of 38.1, and then you had this dimension but it was not in parentheses, I would actually count that as a -5 mistake, because that would just freak the manufacturer out. They wouldn't know what to do. They would be like, well, which of these dimensions should we use to make this part? And here's where that could be a real problem. What if your part's being made in China and you live in Round Rock and you design this part in Round Rock? Well, it's possible that the person making your part here is 12 hours difference in time than you are. So you're in bed out there in Round Rock and there's a machinist in China going, which of these dimensions do I use if you don't make this a reference dimension? Okay, so it's going to stop the process until they figure out which dimensions they're supposed to use. That is a bad mistake. When you stop the presses and you stop the CNC mill from running, that's not a good thing. So that would be a -5 type mistake. All right. Okay, so the new assignments, they're not actually new. I told you needed to do all 4. I'm going to kind of show you those. But the first 2 assignments were the bracket, this guy right here, and of course you're going to be dimensioning it in model space like that. And what I ask you to do is make a PDF of that and send it to me. Put your name in the file name, by the way. And when you send me your email, I want you to say, here's the first draft of my bracket. And what I'll do is I'll look at it and I'll see that you have your dimensions and I'll send you back the check print. So I've done that with like maybe half the class now on the bracket. So then what you want to do is make your changes after looking at the check print and make a new PDF and send it back to me. And this time say, here's my final bracket. So I know that this is the one I need to grade. So the first one you send me, you could say, here's my first draft of the bracket. Please send me the check print if you wanted to. I'll send you the check print. Now remember, the check print is sort of like almost a perfect drawing that you can compare your drawing to and try to find your own mistakes. So once you've done that with the bracket, you want to do the same thing with the shaft guide. You want to print it as a PDF, email it to me and say, here's the first draft of my shaft guide. Now, one thing I want to point out to you is the text height here. Just remember that the text height on this guy is 3 millimeters. And so somebody said, well, how do you put this text in here? On your annotation tab, if you pick on this down arrow, you have this tool called multi-line text. Just come in here and draw a box like that. And then you can start typing inside that box. If you highlight that text and you look right up here, you can see mine says 2.5. So what I want to do is highlight that and type 3 and press enter. And what that does, it changes my text to 3. And then I'm going to come in here and I'm going to type this note. Now the note should be Arial font. And the 3 text height should match the 3 text height here in your dimension style when you're doing that. So I'm not going to save that. But so remember, to change your font, you're going to go to Format. You'll go to Text Style. You have the standard text style over here. You want to change your font to Arial right here. So be sure you do that. Now, the other thing, when you click in here, you see where it says drawing number? When you go in and edit your drawing number, what I would like for you guys to write right here is the section number. And the section number for this class is 06417. So you would double click on this and type 06417. And that's the section you enrolled for, 06417. That way, when you send it to me, I can tell your drawings from the drawings from my other section of 1405. So it'll help me out a little bit. So what you want to say here is that this is sheet 1 of 1, because it's a one-sheet drawing. You'll write Austin Community College here. Your scale will be 1 to 2. And of course, it'll say Shaft Guide. And right here where it says A student, that's where your name goes. So you're just going to replace A student with your name. If you have a long name and it goes outside the boundary here, the border, I'm going to mark that as a -1. So what you're going to have to do is either use your last name or your first name or your initials so that you don't go outside the border. Okay? So I've had a couple of students already write outside the border with their name. That's not allowed in an office. Okay? All right, so here come the next 2 assignments. We have the tool holder, which looks like this. And this is a good place where you could use your baseline dimensions. And so let me show you about that. If you place your first dimension using a linear dimension, and you go from here to here, and you stretch that up and you go 0.4, and you get your first one placed. Looks like that didn't quite go to 0.4. 0.4. All right. Now, I don't know why I'm getting 0.49 instead of 3.5 in that, but I'm going to keep going forward with it. So I've placed that first one using linear, right? But I want to use baseline dimensions. So here is my baseline tool right there. So the next pick is to pick baseline, and look what it does. It comes right off that first point, and I just pick right there. Then I go over here and I pick right there, and then I press escape. And there are my dimensions. Now remember, this guy has to be a reference. All right, so you may be saying, well, why does that have to be a reference? Well, the reason it has to be a reference, I'll get this over here, is because we know 3 dimensions about this. We know that we have this distance of 4 right there. Then we know we have this dimension right here from that where the 4 ends to the center of this. And then we have this radius right here. And all 3 of those are going to get toleranced. So if we give our overall length, that has to be a reference. And so you would see that in the check print, and it will be a reference dimension. The other thing about this one is, remember that we dimension cylinders. And this is a cylinder right here in the side view. We dimension cylinders in the side view like this, not in the round view. So we have to put that in there. So when you use your linear dimension to do that, and you come up here, wow, this is crazy. This thing's all off 1/100th of an inch for some reason. But here's what you want to do. You need a diameter in front of that. So remember that to do that, you can double click on the dimension, and then look up here in your ribbon and go right here where it says symbol and pick on that down arrow. And you have a bunch of symbols. You could have a degree symbol, a plus or minus, or you can have a diameter. If you pick diameter, that'll put that diameter right in front of it. Let me point something out to you about that symbol. If you pick on the down arrow, you see where it says diameter? To the side of it, it says %C. Back in the old days of AutoCAD, they didn't have a ribbon for one thing, and they didn't have a way to do symbols. So the way you got a diameter in is you actually typed %. Let me close this. There's my cursors right there. I'm going to type %C. And what AutoCAD would do is automatically convert %C to a diameter symbol. And if you wanted a degree symbol, you would type %D. Like I said, this is back in the dark ages. But the point is, that stuff's still in there. There's a lot of that old DNA still in AutoCAD. And so some people still like to type %C when they need a diameter, or %D when they need a degree symbol. So I think it's cool to know that stuff, though you don't have to, because you've got the symbol option. All right, so that is the third drawing, and then the fourth drawing is this guy right here. This is your tool slide. And I think the thing you want to watch out for is this. If you look on page 299 in your book, because that's where this assignment is laid out, is on 299, and you look at the sketch, and you look at the distance in the front view between this edge and this edge, and you look at that in the book, you're going to see that your designer said that needs to be 2.250. The designer took that to 3 decimal places. So what that would make me think is, if they're tolerancing the width of that piece right there to 3 decimal places, then it may fit into a slot or something, and that slot is toleranced tightly, okay? So you've got to make sure when you put this 2.250 in there that you go to 3 decimal places on that, even though the dimension next to it is 2 decimal places. Okay, so we have 2 different tolerances on those 2 dimensions right there. And if we go down here and we zoom in, we can see that dimensions taken to 2 decimal places are plus or minus 0.2, and dimensions taken to 3 places are plus or minus 0.1. So we've got to pay attention to when it's 3 places and when it's 2. The overall height of this part is going to be a reference dimension, because we've got enough dimensions to make the part. We don't need this dimension right here, but if we give it, we're going to give it as a reference. All right. I think that is everything that I need to cover as far as showing you AutoCAD and talking about tolerancing. So I'm just going to go back into Blackboard, click on Chapter 5, and this opens up. And so what I suggested at the last class meeting is that you watch these 3 videos right here on dimensioning basics, part 1, part 2, part 3, and they just talk about spacing and dimension, the ASME and things like that. But now what I would recommend watching is the 3 videos on tolerancing basics. These are the important ones that I talked about today, except I'm going to, slow down and walk through them a little bit slower and really explain what's going on. If you want to be a designer, you need to understand what's in these 3 videos right here, okay? And you can watch them, this weekend, or you could watch them next week or the week after. Just remember, this is all important stuff in here. This is where you make your money, I think, once you get an industry, is understanding dimensioning and tolerancing. All right, so when you scroll down, though, you're going to see the assignment folders. And a lot of you guys have done the bracket, but the 2 I'm suggesting that you get done now, hopefully you've got the other two in pretty good shape, are to open up the tool holder. There's a video on creating the dimension style for the tool holder. And then there is a video on adding dimensions to the tool holder. And then if you back up one level, you've got the same situation for dimensioning the tool slide. You have a dimension style, and you also have a video on dimensioning the tool holder. I'm sorry, the tool slide. Now, somebody emailed me, and I think after they made the dimension style for the bracket, they thought that the dimension style would still be there when they opened up, the next project. AutoCAD doesn't work that way. If you make a dimension style, it just belongs to that drawing. Now, that doesn't mean there's not a way to get it in. It's just that I haven't taught you that yet. And so the reason I haven't taught you how to do that is pedagogically, we want you to make 4 different dimension styles because we're trying to get this into your long-term memory for how to make a dimension style. And if you just make it once, like 3 weeks from now, I'll say, make a new dimension style, and you'll go, dang, I know we did that, but I don't remember it. We're hoping that by making 4 dimension styles, it will stick into your long-term memory, because it's easy to get stuff into short-term memory, but it takes repetition to get it into long-term memory. That's why we're making you make 4 different dimension styles. All right. Okay, with that, I am definitely done. And so if anybody has a question they want to ask, feel free. And if anybody is signing off right now, then have a great weekend. The assignment is to get all 4 of these done and dimensioned before next Tuesday. And the reason for that is that on Tuesday, we're going to open up the guest cottage, and we're going to dimension the guest cottage, and we're going to talk about dimensioning architectural projects. So we need to get these 4 mechanical dimensioning projects behind us this week. Okay, we will continue to dimension everything we draw from now on for the most part. So you're going to get more and more practice dimensioning, but this week was all about dimensioning those 4 projects. All right, so try to have them done by 11 o'clock on Tuesday so that you can focus on the guest cottage dimensioning project on Tuesday. Okay, that's it. If you're going to stick around, I'll stick around till 12:40 today. And otherwise, have a great weekend. I'll be looking for your PDFs that you're going to send me. And remember, it'd be helpful if you say, here's my draft of this, and then here's my final version of this for a grade. Always put your name in the name of your PDF so I can keep yours apart from other students. Okay, thank you, and have a great weekend, or stick around and talk to me.